So, short introduction to testing for normality. So suppose we have a population we're studying and we've taken a sample from that population. So we have a sample, X1 through Xn, a sample from the population. And we want to know, on the basis of this sample, do we think that it's reasonable to infer that the population is roughly normally distributed, or do we think it's more reasonable to infer that the population is likely not normally distributed? Why is this important? Well, one of the reasons is, just like we said up here, we suppose that men have weights that are normal with this mean and standard deviation, and we're looking at an average of size 16. Well, we're leaning pretty heavily on this presumption that the underlying distribution is normal here. If it wasn't normal, this sample of size 16 is really nowhere near the sample size of 30 that we want to satisfy our rule of thumb. We'll also see later on for some of these other sampling distributions. I was on the other page, but remember I mentioned there are different sampling distributions. Well, different sampling distribution results and different, confidence interval and hypothesis test results and so on that build off of those have different amounts of tolerances to deviation from normality, right? So I can apply this result of the central limit theorem to a population that's not normal. And even if the population deviates pretty significantly from normality, if I have n bigger or equal to 30, I can still apply this. But there are some of them, like, for instance, the sampling distribution for, say, the standard deviation or the variance, where we really have to lean heavily on the underlying population being normal for things to work out properly. And if the underlying population is non-normal, that becomes a much bigger problem in some other contexts. So we might be really interested in making an educated guess about whether or not the underlying population is normally distributed on the basis of a sample. And there are basically three approaches. And this is an increasing order of complexity. There's the so-called back of the envelope test. And it's not like the back of the envelope test, but a back of the envelope test is basically kind of a quick and dirty way to get a pretty decent idea of what's going on. That's what a back of the envelope test generally means. So it's a little reminiscent of something like, say, the range rule of thumb, right? Where we say the range is about 4 standard deviations. The standard deviation is really annoying to compute. The range is really easy to compute. So if I just say that a standard deviation is about 1/4 of the range, that's kind of a back of the envelope estimate for the standard deviation. It's quick and dirty, not super accurate, but maybe gets me in the ballpark of a right answer. Second, I can look at something called the QQ plot. And this is what we'll address in the PowerPoint presentation next time. And the third is, well, we have formal tests. So we have things like the Kolmogorov-Smirnov test, the Anderson-Darling test. There are formal tests where you do a bunch of computations, you get some number that's related to your data, you compare that to some number that's some kind of standardized number, and you see where the one number falls relative to the other, and that gives you a claim. It gives you a claim that either the population seems to be normally distributed or the population seems to not be normally distributed. We're not really going to talk about these formal tests. I'll kind of briefly give an idea of what a formal test structure might look like when we talk about the QQ plot. But for right now, we're going to focus on these back of the envelope, or this back of the envelope test idea. So what's the idea of the back of the envelope test? Well, the logic goes this way. If the population is normal, then I expect the following. I expect it to be, well, what were our three characteristics of a normal distribution? I expect it to be symmetric. I expect it to tail off to the sides. And I expect it to basically look bell-shaped. In other words, if I expect to see symmetry, I would expect that the Pearson coefficient is between -1 and 1. If I expect it to tail off, well, one way that I could think of tailing off, something that doesn't tail off to the sides, is something that has a lot of meat in the tails, far away from the center of the distribution, right? So in other words, how what percentage of my data points fall within one standard deviation, two or three standard deviations? I expect it to follow the 68, 95, 99.7 rule. I expect rough concordance with that rule. If I look at the proportion of data points that are within one standard deviation of the sample mean, one sample standard deviation of the sample mean, then I expect that to be about 68% of the data points, 68% of the sample size. Similarly with two standard deviations and 95%, 3 and 99.7%. And then bell shape, just looking at the histogram. So I say if it's normal, if the underlying population is normal, then I expect the sample to roughly follow these three criteria. If I see substantial deviation from these criteria, then that would lead me to conclude that the underlying population is probably not normal. Okay, so let's bring up this Excel file with some of the data and we'll investigate some of these data sets. Okay, so this first one is S&P data. These are some S&P 500 monthly returns ordered from most negative monthly return to most positive. And again, what I might want to look at is, say first the histogram. And it's a little hard to tell on a histogram like this. We can maybe split up more bins, but we do see kind of a peak in the middle and kind of a tailing off to the side. So again, this is a back of the envelope test. It's rough, it's dirty. It's not, we're not expecting a graph that's going to look like a perfect, textbook normal distribution. But does it look like it's right skewed or left skewed, or like clearly just going from bottom left to top right, or vice versa? Doesn't really look like that to me. It does look like it kind of peaks in the middle and has some tails along the sides. So I don't see any big red flags yet. I'll compute my Pearson coefficient next, looking for skewedness versus symmetry. This is 3 times the mean, which I've computed up here, minus the median, which I'll just compute in line. So 3 times mean minus median, make sure those are in parentheses, over standard deviation. Let me actually double check that I actually have the right things here. Yeah. Make sure I didn't have some vestigial mistake or something. And I see my Pearson coefficient negative 0.19 or so. That's certainly between -1 and 1. I see no evidence of skewedness. So no evidence of skewedness. The histogram looks in the ballpark of what I would expect. And then let's check the empirical normal rule. So for the different standard deviations, 1, 2, or 3 standard deviations, what's the mean minus 1 standard deviation? That's mean minus this many standard deviations. When I drag down, I want my mean to stay the same, and I want my standard deviation to stay the same. So down here, I see I have mean minus 3 standard deviations. And then for the mean plus 3 standard deviations, so mean, and I'll block that, plus this number of standard deviations. Oh, and again, I'll drag those down, just double check, and it looks like everything worked out right. And here I'll just kind of count. So I want to count, I've already sorted them in order. So I want to count everything from negative 3.35 up to positive 4.65. So starting here and going up to there. This will just give me the number of data points that are within 1 standard deviation of the mean. And I could maybe come up with some fancy formula to type in here, but in this case, it's just easier to code it in like this. So here I want to count all the data points with a value between negative 7.3 and positive 8.6. So that's everything from the lowest number up through everything from 1 below the highest. And then negative 11 to positive 12 includes everything. And the percent is this number over 23, which is our total number of data points. And then we'll just do times 100 to make it into a percent, a little easier to read. Oh, why did it do that? Excel is usually good at guessing what you want it to do, but sometimes it does crazy stuff like that. So these are the actual percent of the data points that fall within 1, 2, and 3 standard deviations. What would we expect to see? We'd expect to see 68, 95, 99.7. And that looks pretty darn good. You might say the 78 versus the 68 is maybe a little far off, but really what we're worried about here, practically speaking, what we're worried about is that we get outliers more often than we expect. We're practically not too worried that there's a little more meat near the mean. We get more worried, we experience more problems if there's too much weight in the tails, more than there should be. So what do we see? We see decent adherence to the empirical normal rule, the general kind of fit, the general, tailing off or not having too many outliers. We see lack of evidence of skewedness, so the symmetry kind of seems to be working nicely. And again, this is a very coarse histogram. If we wanted to, maybe we would split each of these bins in half or something and get something a little more refined, but the histogram looks good enough. I don't expect it to look like a perfect normal distribution with only 4 bins, but I do see that it kind of peaks in the middle, tails off to the sides. It looks, very roughly in line with a bell-shaped distribution. It doesn't look bimodal. It doesn't look heavily skewed or like it's just going bottom left to top right or vice versa. So this one, I would probably say, okay, I would probably be happy calling this, or happy presuming that this data set came from a normal distribution, normally distributed population, and then being able to apply whatever results of central limit theorem or anything like that I might want to apply. And here is for this one, I refined this a little bit for the histogram, and you can see that by using more bins, we get something that looks a little bit nicer. There's a little clearer of a peak in the middle and tailing off to the sides. Again, does it look like a perfect normal distribution? Well, no, of course it's not going to look like a perfect normal distribution with only a sample of size 23 or so. But does it look good enough that I can see that it's kind of more or less symmetric about a mean? The mean is about 0.65. So it's kind of more or less symmetric about these two tall peaks here. Roughly tails off to the sides and peaks in the middle. Yeah, that's probably good enough. When we come back, we'll take a look at this HIV viral load data, and we'll do the same thing with that. So I think that wraps us up for today. I don't think we can get through that in 4 minutes. But last time we had looked at the S&P 500 monthly returns. And we saw that looking at the Pearson coefficient of skewedness, the Pearson coefficient was between -1 and 1, no evidence of skewedness. So that doesn't invalidate the symmetry condition. One of the things that we're looking for from our back of the envelope test. We looked at the adherence to the empirical normal rule, and we saw 95% of our data points were within 2 standard deviations of the mean, right smack on what we'd expect. 100%, 23 out of 23 were within 3 standard deviations. Again, good adherence to what we'd expect. In a sample of only size 23, we wouldn't expect to see any 3 sigma events. If we saw 1, we'd be a little suspicious. If we saw 2, we probably would toss any idea of normality at that point. And as I mentioned last time, the 78% is a little higher than the 68% we'd expect within 1 standard deviation, but typically we're not, practically speaking, very worried about deviations from normality when we have a little too much meat close to the mean. It's usually a problem when we have too much meat in the tails, so to speak, when we have too high a chance of getting a big outlier. And then the other thing is we look at our frequency distribution. And one thing I did point out last time was it is important to note that depending on how you set up your bars, your frequency distribution could look more or less normal for the same data. So we looked at this and we said, that doesn't really look like a normal distribution. I mean, I guess maybe if I kind of blur my eyes a little bit, I could see kind of a peak and tailing off. But if I use a different set of bins, it looks a little more like a normal distribution. So we're not looking for kind of a perfect bell shape. We're not going to get that with an N of only 20 or even really, 50 or 100, even if it came perfectly from a normal distribution. Just the random sampling is going to bounce things around a little bit. But this would be, I think, close enough. And even this would be close enough for me to be probably okay with calling this a normal distribution. So again, the things that, that I wouldn't want to see are something like strong bimodality, like a hump, a dip, and then another clear hump, or like continuing to go from bottom left to top right, like if this rightmost bin was taller than the other 3, or the other way around, going from top left to bottom right, I might be more skeptical. But here I do see kind of a peak and then tailing off to both sides. I'm probably pretty happy with that. So I would conclude that I think it's pretty reasonable to move forward under the presumption that the population that this data came from was normally distributed. I'm trying to be careful how I say that, because we're not really saying that data is normally distributed. We're trying to say, on the basis of the data, do we think the population is normally distributed? That's really the question we're asking. Do we think this sample came from a normal distribution or not? And we're also kind of on the back of the central limit theorem, we're kind of taking normal distribution as somewhat of a default distribution. So unless I see good evidence that, that I have some skewedness, or that I have something very not normal going on, then I'll move forward under the presumption of normality. Remember, the central limit theorem kind of qualitatively maybe says something like, when we're measuring a characteristic that is the result of averaging together lots of small influences, then that characteristic tends to have a normal distribution in the population. And a lot of characteristics fall under that general description. Okay, so that was a quick review, I think. Oh, I cleared these off last time, but then I think I forgot to save my file last time. So let me just clear these really quick here. Okay. So here I have a set of RNA levels for the HIV virus for different patients. We're going from 3 to 22, so that's what, 19 data points here, or 20 data points, I guess, because we start at 3 and then go up to and include 22. And I named my data. So that way we can do these computations a little faster. We have our standard deviation. stdev is just the deprecated stdev.s function. That's the one from older versions of Excel. I just haven't changed it. And then our Pearson coefficient, remember, is 3 times mean minus median all over standard deviation. Now I compute my Pearson coefficient and I see that this is bigger than 1. It's suggesting evidence of right skewedness. So at this point, I'm a little skeptical, right? The first thing that I compute, Pearson coefficient, is suggesting some right skewedness. If we look down at our frequency distribution, this definitely seems like a right skewed distribution, right? I have most of the mean of my distribution over here on these left 2 bars. And then I have like one data point that's quite a bit off to the right and one data point that's really far off to the right. And I note that if I change my bounds using kind of a catch-all here at the end, it doesn't seem to get a whole lot better, right? So if I drill down, note my bounds here going from 0 to 80,000 versus 0 to 500,000. So if I really focus in on this first, maybe 2 bin widths here, if I really focus in on there, I see, even ignoring these kind of 2 out here on the right, or 2 of these ones on the right that are the ones I think are the right outliers, it's still not looking super normal, right? So even if I drill down a little bit, even if I made this, say, a 1 instead of a 3, forgetting about those 2 right outliers, zoom in a little bit, because again, frequency distributions can look, histograms can look different depending on your bin width. It's still looking a little right skewed, even without those 2 very clear outliers. And with them, it's, looking, almost something like bimodal, but that's because this right bin is a catch-all. So at this point, I'm not really comfortable with this being normal. Maybe the other thing that I'll do is maybe I'll compute a z-score for each of these and see how many 2 sigma or 3 sigma events we have in a sample of size 20. So what do I want to do for a z-score? I want to take my data value minus the mean, all divided by the standard deviation. Oh, I forgot to lock my mean and standard deviation cells. So lock the mean, lock the standard deviation, but do not lock the data value, because that's what I do want to change. And so far, so good. I see a 1.5 sigma event, not a really big surprise. But I note this one here. I see a 3.5 standard deviation event in a sample of size 20. Remember, this is the kind of event that I would expect to see less than 1 in 300 times, right? A 3 sigma event is about 1 in 300 times. 3.5 standard deviations is even rarer than that. I would expect to kind of have to have a sample of size 300 or so, or for 3.5 standard deviations, probably closer to 1,000 before I'd see one of these, but I see one of them in a sample of size 20. I have a sample of size 20 and I don't actually see any like 2 sigma events, right? I would kind of expect to see maybe, a minus 2 standard deviations or something like that. I don't see anything on the left-hand side that's larger in magnitude than -1, but I see this +3 standard deviations, this +1.6 standard deviations. So what's really happening here is I have these two huge right outliers. They're influencing the standard deviation, making the standard deviation enormous, which means that effectively all of the meat of my distribution down here in these two bars, the z-score is being divided by some huge standard deviation because of the impact of those outliers. And it's making all of these z-scores really close to 0, except for the z-scores for the two outliers, which are the ones contributing to the standard deviation. If we, just change these numbers just to see what would happen to, let's say, 60,000 or something, and 70,000. Oops, that's 700,000, 70,000. We see our standard deviation got a lot lower, and we do see a nice array of, 1 standard deviation events. We see a -1 standard deviation event. This would be kind of a much more reasonable scenario, right? Still some evidence of right skewedness, again, because even if we drill down into these two bars up here, we still see some kind of right skewedness here, but it's nowhere near as severe, I think. Or it's not, I shouldn't say nowhere near as severe, but it's not as severe. It's not as obvious that this is right skewed. Okay. So overall, I would say that this is something we would definitely not want to model as a normal distribution. We don't see good concordance with the empirical normal rule. We see evidence of right skewedness, and the picture, regardless of which way we set it up with the bins, really just doesn't look right. And so again, this is just a recap of that. Okay, so we have our back of the envelope test. We check skewedness, empirical normal rule, and histogram. And again, that's kind of a quick and dirty thing to do. We can get a rough idea of whether we think the distribution is, or the sample data comes from a normal distribution fairly quickly, without a lot of work and without a lot of really deep technical understanding. We can go to something that's maybe a little bit more objective, maybe a little bit more informative, or at the very least is just a slightly different approach. And we can talk about a QQ plot. Let me try to get this to send over. Okay, so the QQ plot sent successfully. Oh, I just realized, I'll bet the testing for normality didn't want to send because I had it open in Excel. I wonder if that was the reason. But the QQ plot is in the chat, so you can download that. This is a PowerPoint presentation that we'll work through. We're not going to do a ton with QQ plots. We're not going to, I won't expect you to, create them from scratch or anything like that. We're going to mainly focus on if somebody gives you a QQ plot for some data relative to the normal distribution, can you look at that QQ plot and assess whether on the basis of that plot you think that the data do roughly correspond with normal population, or that they don't seem to correspond with a normal population. So here I'm using the statistical programming language R for these demonstrations. But you could use any of several statistical packages. Excel is it's a bit of a pain to construct a QQ plot in Excel, although you can do it. The last sheet on here is actually a construction of a QQ plot from first principles in Excel. So we'll briefly talk about that, but that's not something that I expect you to be able to understand how to do. So just to make the expectations clear, if you were given a QQ plot, I would expect you to be able to look at it and say, do I think this roughly corresponds with a data set from a normal population or not? So that's really what the expectation is here. So here we're going to have R, the programming language, simulate draws from a standard normal distribution. So we know that this data came from a standard normal distribution. So our answer when we say, does this QQ plot, is this QQ plot in line with what we'd expect from a normal? The answer is certainly yes, because we know that we're drawing from a normal distribution. We also have an enormous sample size, n equals 10,000. So this is like best case scenario. You know, perfect random draws because we're using the software to simulate random draws, perfect random draws from an actual normal distribution with a huge sample size. And this is what a QQ plot would look like. So what is this? What are all the pieces here? So QQ plot is a plot of the theoretical quantiles or basically percentiles versus the sample quantiles or percentiles. And another way that we could think about this is the theoretical quantiles would be like expected. In other words, in a theoretically perfect scenario, this is what we would expect to get, versus sample quantiles from our sample data. This would be something like observed. So what did we actually observe? So what are we kind of doing to construct this plot? Well, here's what we would do. We would take our data set, x1, x2 through xn. Oh, let me move this down a little bit, get a little more room. For my data set, I can compute x bar and I can compute s. So then for my data, I would compute z-scores. In other words, z1, z2 through zn. So these are my observed z-scores. Oh, and x1 through xn are ordered. So we're assuming that we've sorted them from smallest to largest already. That's kind of an assumption we've been working off of since we started talking about medians and so on. So these are already sorted in increasing order. Now what I do is I take my data and I go back to chapter 3 and I say, what's the percentile for each of these data points? Maybe if I have 10 data points, I see that x1 kind of covers the region from 0 to 10%. So maybe it's like the 5th percentile, and then x2 would be like the 15th percentile, x3 the 25th percentile, and so on, right? So I go through and I say, what are my percentiles? For instance, 5th percentile, 15th, 25th, down to 95th, or something like that, right? If I had a sample of size 10, if I had a different size sample, this list of percentiles would be different. And now I can ask the question. So this is all based off of my data, but now I can kind of shift my thinking and say, okay, well, I know how to compute percentiles of an actual normal distribution, of a standard normal. So what are my standard normal indices that correspond with this list of percentiles? In other words, what's P5, what's P15, what's P25, down to what's P95. Note that these P's are essentially z-scores, right? These are z indices. These are locations on the z-axis for a standard normal. Now, what I see is for a given percentile, I kind of have, if this was a perfect normal, I have a theoretical Z index that I'd expect to see, the fifth percentile of the standard normal. And I have kind of an observed Z score for the fifth percentile of my data. If my data were perfectly representative of a normal distribution, these two numbers, Z1 and P5, I guess I called it. Again, this would only be P5 if we had a sample of size 10, right? But I'm just using that as an example here. These two should correspond exactly. These should be the same number. And the same with these two. If my data set was a perfect representation of a normal distribution, then its second z-score, Z2, should correspond directly to that second percentile on the list of, or that second Z index in the list of the standard normal percentiles. So in other words, I have paired data, Z1, comma, P5, Z2, comma, P10, down to, I guess it would be Z10, comma, P95. I have a set in this case, say, of 10 ordered pairs. Or if I had a sample of size, 55, I'd have 55 ordered pairs or whatever. Sample of size 10,000, I have 10,000 ordered pairs. I'm going to plot these ordered pairs. My theoretical quantiles are my P sub whatevers, and my observed are my Z whatevers. So I guess I'm kind of doing the ordered pair in the opposite direction. The way that I wrote them down here, my first coordinate is the vertical coordinate and my second is the horizontal. It doesn't much matter which orientation, which we'll see in a minute why it doesn't much matter which orientation we're plotting them in. But I would plot, say, Z1 and P5. Maybe that's a point here. I might plot Z2 and P10. Maybe that's a point here, and so on. Now, remember what I did down here. I said, on one hand, I have Z indices for my actual data. And on the other hand, I have Z indices for a theoretically perfect standard normal that's at that same percentile. If my actual data set is a perfect representation of a normal distribution, then my Z's will be, my Z1, Z2, et cetera, will be a perfect representation of a standard normal distribution because I've standardized them by getting a Z-score. And the Z's and the P's would exactly match up one at a time. In other words, in the perfect scenario, they would fall perfectly along a 45-degree line, along a line with slope 1. Because this number would equal this number, and this number would equal this number, and so on. So what would I do with my QQ plot? Well, what I do is I draw a line. I draw this line with slope 1. That's the kind of theoretically perfect line. And then I plot as a scatter plot on top of this line, this list of ordered pairs. So I might have one that looks like this, and then like this, and like that, right? If I see that my scatter plot, my list of my set of points representing these ordered pairs, roughly fall along this slope 1, this 45-degree line, if they fall very close to it, I'm quite confident that this data set came from a normal distribution, that it's a representation of a normal distribution. If they were to instead, say, deviate from this line in a way that's either, substantial or where there's a pattern, like say high, low, high, then I would be skeptical. I would say that I think that there's a lack of normality here. So kind of the best reasonable case scenario, I mean, of course, the perfect scenario is everything falls exactly on that 45-degree line. The best reasonable case scenario is most points fall pretty close to the line, and the deviations are effectively random. Whether they fall above or below is kind of random. The things that would give me pause for calling this a normal distribution would be if I have significant deviations, substantial deviations from that 45-degree line, or if the deviations occur in a pattern where I have like, a bunch of deviations in a row that are above the 45-degree line, and then a bunch that are below the 45-degree line, and then a bunch that are above, right? Where there's a clear pattern. It's not randomly assorted between being above versus below. So that's the idea of a QQ plot. So now looking back over here, this plot should make a little more sense. We have our 45-degree line here, which we can almost not even see in the middle, but we can, if we look at the top right or bottom left, we can kind of see that there is actually a 45-degree line there. Keep in mind, this is like the best case scenario from a normal with a huge sample size. So we're looking at like the best QQ plot you're ever going to see, the most strongly indicative of a normal distribution you're ever going to really see. And I see that these data points here, these ordered pairs that are graphed, I mean, there's 10,000 of them, so they start to just like line up on one another and just look like a black line. But we can see again, bottom left and top right, that these are actually individual circles that are plotted. There's just 10,000 of them. We see that these fall like right on this 45-degree line. I'd be very comfortable modeling this, or I'd be very comfortable if I looked at this QQ plot saying that this data likely came from a normal population and modeling this population as a normal distribution. If I look at a histogram, again, this is like the nicest histogram you're ever going to see. This is perfectly random draws from a normal distribution with a huge sample size. My histogram looks very much like a normal. Okay. So these first couple of slides are like, textbook case, not even textbook, because it's like you'll never see this in the real world. This is like, theoretically perfect case. Okay, so what if we had something a little more reasonable? Drawing from a standard normal distribution. So we do have a normal distribution that's underlying this. We are getting, nice random draws. We're not introducing, observer bias or anything like that, because we're having the computer program do the draws randomly for us. But here we don't have quite as big of a sample size. We have a sample size 200. It's still a pretty big sample size when you think of sample sizes that we typically would see, but not as big as the 10,000. As an aside, this is what the R code would look like. So in R, we take random draws from normal distribution, standard normal of size 200. We store that in the variable X. Here's a printout of what all of those draws were, just in case you're interested. We had 200 draws, and if we look through here, these are all Z-scores. We do see, maybe about 5% of these or so are plus or minus 2-ish. I don't think we see a 3 standard deviation in here, at least at a glance, but you can, these are basically just Z-scores, right? So you can think of this relative to like the Z-scores for the HIV viral load example that I mentioned. We don't even see, I don't think, a single 3 standard deviation event in here. And this is for a sample of size 200. This QQ norm and QQ line actually are just built-in functions in R because it's a statistical programming language. It does a lot of these stats things very quickly and easily for you. So these 2 commands make the QQ plot. The rest of this, calculating the mean, the standard deviation, the histogram, and so on, that's all for computing this picture. But we can actually get a QQ plot out of R with just these 2 lines, QQ norm and QQ line, and there's our QQ plot. So super easy to do in R. Again, you can do this in Excel, but you have to basically make this chart from scratch. It's, you know, a good bit of work. It requires a good bit of background understanding about what you're doing when you're constructing the QQ plot. So what would a very, very nice QQ plot look like? Again, perfect random draws from a normal distribution, sample of size 200. This is what it would look like, right? The middle corresponds very nicely to the 45-degree line, to that slope 1 line. The edges get a little bit fuzzy, but this is about the best that you would hope to see. This would be kind of what I would call the textbook case. If we look at our histogram, again, this is like the textbook case, like the best histogram you would, you know, practically see in any kind of realistic scenario. We see our normal curve with the same mean and standard deviation as the data, and we see that there are some blocks that are a little lower, some histogram boxes that are a little lower, and some that are a little higher than we'd expect. But we generally see the peak in the middle, tailing off to the sides, kind of more or less symmetric. We're not going to get a perfect adherence, even in a very, very good situation. So what does a bad one look like? Well, here, let's look at drawing from an exponential distribution. An exponential distribution is very not normal. I mean, in some sense of the term. An exponential distribution looks like this. It's only defined for positive values. It's extremely right skewed. The meat of the distribution is here, but it has this infinitely long tail to the right, so it's very right skewed. The normal distribution is symmetric. This is very right skewed. It also probably has a what you would call a heavier tail than the normal distribution. I don't think we would quite call this a heavy tail distribution, but it's certainly a heavier tail than the normal distribution. The normal distribution has extremely thin tails. And lambda is a parameter, kind of like mu and sigma are parameters for the normal distribution that allow you to fit the model to different scenarios. The exponential distribution has a parameter, it's called lambda. So this is a decidedly not normal situation. If we take a sample of size 200 from a random sample from an exponential distribution, REXP is the function, we do the same calculation we did before. Well, now we see our 45-degree line is actually kind of at the bottom here just because of where it, because of where all of these data points kind of ended up. We see there are a lot of data points substantially far away from the 45-degree line, these ones on the top right and on the bottom left. And we also see a very clear pattern that on the bottom left, our sample data is all above the 45-degree line. Near the middle, they're mostly below. And on the right side, they're all above again. So I see substantial deviations from that 45-degree line, and I see a pattern in the deviations. The pattern like this is indicative of the right skewedness, and the substantial deviations are indicative of the just really generally not matching normality. If I tried to overlay a normal distribution, which is this dashed curve here, with the same mean and standard deviation as this data set has, if I try to overlay that on a histogram of the data set, I see very clearly this is not normal. I go from top left to bottom right. I see that there's not a symmetry. There's not a peak in the middle tailing off to both sides, right? This is a very clearly not a data set that came from a normal distribution. But the QQ plot, I can look at this one plot and see that I have substantial deviations and a pattern in the deviations. So I would not be comfortable modeling this population as a normal. So what if we draw from a uniform distribution on -10 to 10? Recall that the uniform distribution, flat across here, this is symmetric about 0. So it does share that characteristic with the normal distribution. It has a nice symmetry to it, but it doesn't have the peak in the middle tailing off to the sides. Um, it's unlikely to follow the empirical normal rule. It doesn't really break the symmetry, but what would it look like whenever the tails in the center don't match up correctly? Again, I'm going to take a sample of size 200 from a uniform distribution going from -10 to 10. This is the random sample that R cranks out for me. And I compute the QQ plot and the histogram. And I actually see, because of the symmetry, I actually see that in the middle here, I get actually pretty nice, pretty nice adherence to the theoretically optimal line. So from on the theoretical quantile side of things, maybe from say -1 to +1 or so, if I just clip this, if I only looked at, let me actually do it so I can show you exactly what I'm talking about. If I actually just showed you this chunk of the QQ plot, you'd say, oh yeah, normal distribution, no question. But where we really see the deviation is out here in the tails, in the high or low z-scores. So one note that I should point out is when it's saying sample quantiles here, R is not doing the z-score thing from the data. It's just using the data itself, which is why we're not getting, we see that the sample quantiles are like -10 to 10. So, I mean, I set it up over here in a way that I think would, number one, that's equivalent. You're going to get the same answer in a very similar looking graph in either case. And number two, in a way that I think is easier to understand what's going on. But just essentially for efficiency, R isn't going to convert everything to z-scores first. It doesn't affect the picture at all. It just affects what this vertical axis is doing. So I just wanted to note that. You might have noticed that on the exponential distribution as well, that it goes from like 0 to 5. It doesn't, there are no negative numbers there, and that's why. But anyway, so in the middle here, we see very nice adherence to the kind of perfect normal line. But at the ends is where we start to see both substantial deviations. So thinking of, say, vertical deviations from the line would continue up to, where this maybe like editing, box is. But our actual data kind of tails off and hits kind of a cap and gets stuck. It doesn't follow that line up to the right or down to the left. And again, we also see a pattern. We see that the data points on the bottom left are basically all above this line, and on the top right are all below. In the middle, we have nice adherence, but those tails are what are concerning to me. We're probably going to have too high of a likelihood of getting a 2 or 3 standard deviation event than we'd expect from the empirical normal rule. On the basis of this QQ plot, I see substantial and systematic deviations from the perfect normal line. So I would say that on the basis of this plot, I don't think this data came from a normal distribution. And of course, if we look at the histogram, we can see that, and keep in mind, this is 200 sample size 200 from a uniform. It's not going to be perfectly straight across, right? This is what like, real world data is going to look like. Even if it comes from a uniform, it's going to be jumbled about like this. Some people don't realize kind of how much randomness, or how much different from the theoretically perfect scenario things can look whenever you're taking random samples. But we see that certainly this histogram does not mesh with a normal curve with the same mean and standard deviation. And this is just kind of, this isn't really an informative example. I think it's just a pretty picture. What about perfect draws from uniform distribution on -10 to 10? So what if we start with -10? Well, What if we start with -10, work our way up to +10, and we go in increments of 0.1? So what if I would have 201 draws from a uniform distribution that are perfectly lined up along that uniform distribution. I actually just think the picture looks kind of cool. Um, so again, we still see very nice adherence between about -1 and +1 on the theoretical quantiles, but we see that same kind of systematic and substantial deviation on the top right and bottom left, so not from a normal distribution. And this would be our perfect uniform histogram. There's a little bump over here just because one of the bins had to be a catch-all and take on the extra one, right? Going -10 to 10, we have kind of a symmetric bit for the positives and negatives, but then the 0 kind of throws an extra one data point in there, and that data point got caught in the catch-all bin on the left, but we see basically a perfect uniform. And now we're going to look at the QQ plots for the two data sets that we looked at here. We looked at the S&P data, which we thought was probably reasonable to model as a normal. And we looked at the HIV viral load data, which we thought was probably not reasonable to model as a normal. So if we input this actual data into a variable X, and then we do the same thing, QQ norm, QQ line, make a histogram and a normal curve. For my S&P data, I see here's my kind of theoretically perfect line, this 45-degree line here. I see in the middle, everything matches up very nicely. I have one point on the top right that seems to deviate a bit from the 45-degree line. I have 3 points on the bottom left that seem to deviate a little bit. I don't think, in my interpretation, this is enough to call it a systematic deviation. I mean, there are 3 points in a row on the bottom left that are below the line, but it's not like there's 7 or 8 points in a row that are below the line. If I look at the majority of the data, they kind of bounce between being above and a little bit below. On the top right here, I only have one data point that's above the line, and it doesn't seem to be that far above the line. It doesn't seem to be so far out of line with everything else. Again, I'd probably be fine with calling this normally distributed. And again, looking at the histogram relative to a normal curve with the same mean and standard deviation, this looks pretty reasonable, especially considering, keep in mind that kind of the best reasonable case scenario would look something like this. So again, I would be probably pretty comfortable calling this population normally distributed on the basis of this data set. If I look at the HIV RNA levels, doing the same thing, entering the data into the variable X, making the QQ plot and the histogram. Now I see my kind of theoretically optimal line, my 45-degree line from over here. I see much more substantial deviations up here on the top right. I see 4 points in a row that are above the line. Then in the middle here, almost all the points are below the line. And then on the right, these 5 points in a row are above the line. These two on the top right are definitely substantial deviations. So this one, I would probably be very uncomfortable modeling as a normal. I see substantial deviations and I see a very clear pattern. Above, below, above. That's indicative of that right skewedness. That's the kind of thing that we saw with the exponential distribution, right? That's a strongly right skewed distribution. In fact, looking at the QQ plot for an exponential distribution against the normal and for the HIV viral load against the normal, I might even think to myself, maybe I ought to model this as an exponential distribution. This looks like the kind of QQ plot that I would get for an exponential distribution, comparing it to normal theoretical quantiles. And then, of course, if I overlay a normal curve with the same mean and standard deviation, it really doesn't look anything like the histogram of the data. So that is QQ plots. One other thing that I would like to note is we've only talked about QQ plots comparing our data to a normal distribution. But for these theoretical quantiles over here, these percentiles, could I have, instead of comparing these to the 5th and 15th or whatever percentile of a normal, could I have compared it to an exponential distribution or to a uniform distribution? Sure, I could have done that. I can actually use a QQ plot to compare my data to any theoretical distribution I want to see if I get good adherence on that 45-degree line. So if I were to look at this and say, based on the way that my plot looks comparing my data to the normal theoretical quantiles, I might think that an exponential might be a good fit for this. What would I do? I would take the exponential family of functions, like the normal. I would figure out a way to estimate lambda based on the data. Lambda would end up being 1 over the mean of the data. And then I would refigure out my standard exponential percentiles and compare those with my data on a different QQ plot and see if I get a good adherence there. And based on this picture, I would kind of expect to. So that's just kind of an aside. Now you might say to yourself, well, this still seems kind of subjective, right? Could a reasonable person look at this QQ plot and say, well, I have a pattern of deviations, 3 in a row below, 1 above? Maybe they look at that as a similar pattern to the below than above. Is this one up here? Is this one up here substantial enough to be worried about? Maybe two different people would disagree on that. Oh, wanted to move up over here. There we go. So one thing that we could, and this is just going to be we're going to speak in very broad strokes here. So here's our 45-degree line. And we have our points that maybe look something like this. One thing that I could ask to make this a little more objective, I could say, well, if my points are generally quite far away from this 45-degree line, that's kind of bad in a sense. That's indicative of not being distributed according to the model that I'm testing it against. And if they are, for the most part, pretty close to that line, then that's indicative of being distributed according to that model. So I could ask, what are the deviations of each of these points from the line? Or I note that some of them are going to be positive, some are negative, so I could add up, say, the squared deviations from the line, or maybe the absolute deviations from the line, something like that. I could add those all up, and that's going to give me a number. The higher that number is, the greater the tendency that there is that these data points deviate from this curve. And this is bothering me a little bit up here. This should be something like that. This should be, these do need to be a strictly increasing function, just because of how they're set up. So this data point would not have been possible, but something like this would be. So the larger this number is, the more skeptical I am that my data are distributed according to the distribution that I'm testing against. The smaller this number is, the closer to 0, the more confident that I am that my data, or that my population underlying the data, is distributed according to what I'm testing it against. So I can compute this number and then compare this to, say, some kind of standard number, maybe based on the sample size or something like that. I could have a list of kind of standard numbers for different sample sizes, and I could say, if this number is greater than that standard number that I look up off of a table or something, then I say, okay, the data points are overall too far away from the line, and I toss this model as a contender for how it's actually distributed. Or if it's this number that I compute is less than some standard number off of a table, then I say, okay, the points are close enough to the line that I can move forward and I can model my population according to the model that I was trying to use, and I might feel comfortable doing that. So this idea of QQ plot can be formalized even more to something completely objective, where we would compute a number, compare it to some kind of number on the table here. How would you get this number from the table? Well, you might say, like, if hypothetically my population was completely normally distributed and I compare against a normal distribution, sometimes just by random sampling, I'm going to get deviations from this 45-degree line just by randomness. So how big do I expect this number to be kind of typically? Or maybe what do I think the 95th percentile of this number is likely to be if my data are actually normally distributed? Maybe I set that number as the cutoff, right? So that might be kind of where this kind of lookup number comes from kind of some kind of analysis similar to that. So a test like this might be something like the Kolmogorov-Smirnov test. So anyway, that's a way that we could even build off of this QQ plot idea and make it even more objective. But again, there's always a trade-off. This more objectivity, the kind of better behavior of the test, comes at the cost of more technical difficulty, more having to understand the stats a little better, those kind of things. So we're always balancing difficulty with effectiveness. Okay, are there any questions on chapter 6?